Thanks for everyone for showing up. This was originally called an examination of string allocations in IE9 because that's how I kind of did the work. But then I realized I wanted to make it work for everything, and it probably should anyway. So it also works on IE10 and IE11. So what we're going to do is change the name to an examination of string allocations, IE9 through IE11 edition. I'm the director of security intelligence at IOActive. I like Windows memory manager stuff. If you ever Googled me or something, I do a lot of heap stuff. I'm from Pittsburgh, Pennsylvania, the United States. I don't know, just recently I did some car hacking things. I run SummerCon, so if anyone's ever in New York City in June, you should come to SummerCon. It's a good time. Little fact about me, I like cheese. We're going to talk about really allocations and freeing of strings for the reason mainly of exploiting things like use after free bugs and things like that in IE. So we're going to have a brief history lesson. Then we'll dive right into IE9, its core methods, and its data structures. The nice thing is these are pretty applicable to IE10 and IE11 as well. I didn't reverse all those, but my techniques still work. So it should be pretty straightforward. And then I'm going to show you a library that I'm going to release right after Ekoparty on my way home, which I'm calling heaplib2. And it's going to make exploitation, hopefully, a bit easier. Why am I even going to do this? It really started back in 2010 at Black Hat when Nico Weissman, who I assume is a local folk hero around these parts, had a statement in his slides that said something along the lines of IE8 introduced weak heap spray protection, right? And I didn't really understand what that meant, and I couldn't find any public documentation showing how this new technology worked in browsers after IE7. Serterov's heap feng shui worked in 6 and 7 and didn't really work in 8. And I figured if there's going to be anyone who looks at some heap thing, it should damn well be me. Why even do this, right? I think everyone knows that browser exploitation is still pretty popular, whether it's amongst pen testers or attackers. Use after free bugs really end up being the de facto method to exploit browser bugs. People do still use heap spraying, and they're not even using it just in the browsers anymore. They're also using heap spraying in things like Adobe Reader and other applications. So while this is focused on Internet Explorer, I think some of the thought process could be applied to other pieces of software. There's a few pieces of information that if you really want to understand all this, you should probably read first. The first being Nico's presentation from 2010. The library that I wrote is really just an augmented version of Serterov's heap feng shui from way back when. And then if you want to learn about COM objects and things like that, in IE, the Attacking Interoperability by Dowd, Smith, and Dewey is an excellent paper. It's very long and complicated, but very educational. A brief history. Heap spraying seemed to be made popular by Skyline with the MS-04, 040. So we're almost 10 years out from when heap spraying became popular, and it still is an effective method. So these things have lasted a long time, and they still work. Serterov did the heap feng shui, which basically described allocation and deallocation of memory with precision by using strings in JavaScript. The premise was if you concatenated a string, you could allocate memory. If you made substrings, you could force memory allocations. And then finally, you could free chunks of memory by setting them to null and running the garbage collector. And it was super easy to do things like heap spraying, like this, right? You set up this big string, you have an array, you copy that string into that array a bunch of times, memory has your stuff. Hopefully, when you trigger your bug, there's your stuff in memory. And it would be super easy to do this. Each iteration would cause a subsequent allocation of memory. The last slide really wouldn't work anymore in IE 8, and I never got any code reasons why that happened. The Corlin team suggested some variations that worked, but the only evidence that they worked was that they saw their memory populated in debugger. There was no kind of reverse code. Nico also suggested a workaround, which worked as well. I didn't really look at this in IE8, but I assumed if it was actually creating memory when you were doing substrings. But again, I didn't know. And for the Nico count, that's 4 Nicos. On 5 Nicos, we can all clap for him because I mentioned him so much in this presentation. Now we're going to move on to how these strings work in IE9. Every string that you create isn't just a B string anymore. And a B string, for those of you who don't know, is an object, a piece of memory where it has a 4-byte size, the string, and a 2-byte null terminator. These are fairly popular within Windows software and otherwise. You no longer see JScript.dll even loaded in the modules list in Internet Explorer 9, 10, and 11. JScript 9 is kind of their new way of doing these things. The below are the versions of the software I used. They're probably a bit dated, but nothing significant has changed. I've checked with the newest versions that were released. Methods, I always like to start with first. The first thing we're going to talk about are these arena literal strings. So when you do something like var a equals Chris, right? Or you create a new string, or you try to do an unescape. These literal strings aren't allocated by their exact size. So you no longer have the ability to create a string and have it do something like malloc equals the length times 2 plus 6, right? 4 bytes for the size, 2 for the null terminator. That's how it worked in IE6, and honestly, it was a very ineffective method for allocating memory, especially when many strings were used in a web page. I want to say about these arena literal strings is they come from this overall pool of memory. So imagine just a big block of memory, and when you created a new string, it kind of just takes what it needs from this overall block. So you don't have really full control over an allocation. So creating a string with a certain size doesn't really do anything for you because it's not a direct allocation from the back end. It's kind of in this cache. Concat strings are also new objects and methods. Before, when you would do concatenate 2 strings, it would actually get the size of that and potentially create a new piece of memory for that string. That's no longer the case for IE9 and above. What will happen now, instead, is they just keep track of 2 pointers. It's kind of like a linked list. And so it'll say, take these 2, whatever their memory was, as they were probably arena literal strings, keep track of their memory, and then eventually, when you actually need the string, as we'll see later, they'll put them all together and allocate accordingly. But concatenations no longer cause allocations. So here's some pseudocode for concat string. I called the one hand left-hand side and the other right-hand side, right? Because you do like A concat B. What happens first is it creates a concat string object, which is 20 hex bytes from the recycler, as you see right there. And then it creates a new concat string. And this new concat string does something like this. It stores a vtable, as the first D word, and then sets the length to 0, and then makes sure that the overall length for 32-bit isn't above 2 gig, right? Because you're not going to be able to allocate memory like that. And then it assigns the objects accordingly and updates the total length. As you see, when you're concatenating two strings now, allocation doesn't occur. It really is just updating pointers. That brings us to substrings. Substrings, again, don't really automatically create new memory. They'll expand the string if needed. So if you have, we'll see later in the pseudocode kind of how that's done. And again, it kind of is just a reference holder for this new piece of memory. And it kind of looks like this. It has a vtable, it has an end index, it has a pointer to the start of the original string, and it has a pointer to the actual string overall that you're using. Again, this is quite small, so I'm going to put the slides and code up. Again, what's it do? It allocates from the recycler a couple of bytes, and then it says, hey, what's the original string? And if that string is null, it'll actually flatten out the string. So you have before when I was showing you the concat string objects, and it updated the pointers. The first time that you create a substring from a string that was concatenated together, it will flatten it out, and by that, it'll actually take that linked list of pointers and make the string. Actually allocate memory. But we'll see later that it's not completely controllable. But I just wanted to show you here. Here's a very important piece of this algorithm right here. And then again, it just kind of updates some pointers, right? It says, here's where I want to start, here's where I want to end, and it'll be on its way. I'm a color by numbers type of person, so I learn best from examples. So I figured the best would go through an example, and we'll kind of show you how this works. Here we have a string builder. It's unescaping what will end up being some x86 nops, right? Hex 90. It's going to build that to be 100 hex bytes, 256 bytes. From there, we're going to take a substring once and a substring twice, and we'll see how this little piece of JavaScript is actually handled when it comes to thinking about things from a memory management perspective. The first thing, escape and the unescape. You have a new literal string, right, where you'll actually have the % and the U and the 90s. It doesn't automatically get escaped. The first thing it does, right, is because it's parsing your JavaScript, is take this string. From there, it will do this entry unescape, which are these little wrappers for other functions. Finally, it'll convert it to string, and you see that it basically is just creating objects based off that string. No precision allocation occurs. It's just really creating objects so the DOM and JavaScript know what to do with it. From there, when we have this loop of concatenated string, right, if you're going to heap spray, you want to create very large strings to put in memory. The first iteration is the string builder, and it concatenates itself with itself, which is another string builder string. From there, at that point, both objects are going to be concat strings because it's implicitly typecasted them to concat strings so it can manipulate them. And it keeps on creating concat string objects and updating the pointers like we talked about before with the left-hand side and the right-hand side. But again, there's no allocations that occur. It's actually just creating these 20 hex byte objects and updating some pointers. So while you may think that you're creating a big string, in theory you are, but in reality, it's not going to cause an allocation. Next, we're going to take a substring of that big string that we just created. Since this is the first time that that concat string has been passed to the substring object, it's actually going to flatten it out. Remember before with that value is null, which it will be since it's the first time it's used. It will call get sz, which will call JS concat string flatten, And again, that just actually takes the pointers and makes it now a 100 hex byte string. This comes from the recycler. If the string is less than 400 hex bytes, it uses this snail alloc routine. Again, I'm going to release, I think at one point, maybe in an upcoming frac or something, all the reversing I did for these recyclers, which is pretty neat. You can kind of see how they work. But if it's bigger than 400 hex bytes, it'll actually result in a call to virtual alloc. But again, you're not going to have complete precision because it's going to actually try to allocate way more memory than it actually needs in case this operation happens again in the near future. So while you can cause a direct allocation, it's not the exact size that you want. So I think when people would show screenshots of a heap spray working, in reality, yeah, their memory was allocated, but the amount of memory they got wasn't exactly what they were looking for. And you want to be precise when you're writing exploits. You don't want to just hope that they work. You want to ensure that they work. But as we saw again, no direct allocations really occurred from the default process heap. The second substring, since the concat string has already been flattened out and allocated from virtual memory or another piece of the recycler, nothing really happens here. It basically just updates some values with certain pointers. So only the first time that you call substring on an object will it actually result in a potential allocation. All subsequent calls to this method are just going to update indexes and pointers. So while you can't really loop a substring operation with a single object. What's the conclusion? The style of heap spraying that worked, I guess at this point, 8 years ago, not so shockingly, doesn't work anymore. You can't just create a variable with a string of a size you want and get it to allocate that much memory. Even if you're looping and doing other things, it doesn't necessarily work out. And this is really where my research could have stopped because I just wanted to figure this out because I don't think it was actually heap spray protection. While it did protect from heap sprays, I think that Microsoft just re-architected how they did string allocations in JavaScript. And it's actually much more efficient, memory efficient, to update pointers and create objects than it is to be constantly allocating memory. So do we have to give up now? Can we not heap spray anymore? Of course, the answer is no. We're going to figure out how we do that. So we'll talk about the DOM. I think most people are familiar with DOM elements, right? The document object model has these elements, and they usually get allocated from the default process heap, at least in Internet Explorer. I know Chrome has some new stuff they just came out with for individual heaps for tags, but that's not what we're going to talk about today. Each tag has a certain amount of bytes, and I remember Nico had this cool table in his slides that showed the sizes for individual tags. And so I didn't want to completely recreate that. So I'm going to release a script just called getelements.py. It's an IDA Python script. You can just open up MS-HTML DLL in IDA Pro and run this script. And it will get all the tags, and it will tell you, the tag name, the constructor that's called and at the address, and then the call to heap alloc that's called for that associated tag, right? So in IE9, if you have a center tag, it calls cblock element create element and allocates 30 hex bytes. Again, I thought this would be neat. If you want to find objects of a certain size that you can create and control, you can run this script, and it should help you out. The next thing that I wanted to look at was DOM attributes, right? And an attribute is when you do like an anchor tag and then href. Href is an attribute to the anchor tag. These create null terminated strings at times. They also create B strings at times, which we'll see. They last the lifetime of the page, and it appears that you can kind of completely control them. If you want to learn more about different variant types, which different attributes can actually be different variant types in Internet Explorer, the Dowd-Dewey-Smith paper is the paper you should read. I should also mention that in these slides, you'll see notes like cmshtml_1.html. I'm going to release a bunch of example HTML and JavaScript with associated breakpoints you can use in WinDbg. So if you want to recreate this whole research process for yourself, you'll be able to do it, and it can be kind of a learning tutorial for you. And I figured that it's the easiest way to learn this type of thing. So I realized that there were custom attributes as well. While all attributes can have a title element, you can create whatever type of attribute you want. HTML5, I believe, was the supporting feature. So for example, if I wanted to do an H1 tag and have an attribute called wonk attribute and have it have a value of special value, this will actually create memory specifically based on the length of the value here, and it lasts the lifetime of the page, and you can completely control when it happens, and it creates a B string. So you have a D word size, this string, and a 2-byte null, which is cool, right? You can create whatever attribute you want and give it a value, and it will be allocated from the default process heap, which is exactly what you want when you're doing this type of thing. Another neat idea I came up with, which I'm not really sure if it will work, was using attributes specifically to write shellcode. My idea was you could potentially heap spray without using JavaScript at all, which doesn't make much sense because usually you're going to have to use JavaScript to trigger your use after free bug, but I thought it'd be cool. So I created another Python script which will assign shellcode in large amounts to attributes that creates a static web page. So you create this web page on your server. The web page can get really big, but since there's so many repeated values, it'll get gzipped and sent down. So while a 300 megabyte file on your web server will actually be transferred across the wire in a couple hundred bytes because the compression will work pretty swimmingly. So you can create web pages that heap spray without using JavaScript by using UTF-8 and UTF-16. I just thought that would be neat. Static attributes that are provided in the HTML and not created dynamically work a bit differently. As we saw before there, I could do the heap spray without any JavaScript. It would actually create a different variant type, which results in a different type of allocation. So for those, since it was static, that is, it was in the web page before in the HTML, the call chain ends up being, as you see here, which C attribute variant, init variant, and then it'll call underscore heap alloc string. That's not always called. That's only called on special occasions and for static attributes. The nice thing about this is there's no 4-byte size. So if you're trying to overwrite a vtable, which is the first 4 bytes of an object, you have full control of all those. But we don't always want to put the values predetermined in HTML, right? That wouldn't make it reusable or actually usable for the most part. I guess I have a sidebar here. The Corlin team guys figured this out, and they were using the title attribute. The title attribute is special. It's kind of a global attribute, and it uses the call chain I mentioned in the previous slide. So while I'm going to talk about using custom attributes, they use the title attribute. That was really good work on their part. But I think the way I do these allocations result in less overhead because I'm only creating attributes and not full objects every time. Again, you want to know more about variant types and why this all works, read the Dowd-Smith-Dewey paper. Custom attributes. This is where I thought the best thing would be for doing exploitation type stuff. Again, I'm a learn by example type of guy, so I figure what we'll do is go through an example here. Here we have a tag which has an ID of wonk. We get element by ID. we create a new attribute. On that element, we set the attribute that we just created, and then we create a string in JavaScript, and then set the attribute value to be the string we created. And the nice thing about this is you have full control of how much memory you allocate based on the size of the string you pass it. The call to set attribute here at the bottom is the most important because this gives us a gateway to the DOM from JavaScript. As we saw before, causing direct allocations directly from JavaScript is very difficult, and I couldn't find a very good way to do it. But if you actually marshal the JavaScript variable to a variant type, which the DOM uses, it's going to use the default process heap, and it's going to use the exact size that you kind of give it. So this, the lazy allocation kind of ensures that this works at a per request basis. So I traced the call chain for creating a dynamic custom attribute like I did in the previous slide, right? And it had a pretty long call chain, but eventually I saw that at one point it called the app_data alloc cached mem. And I instantly recognized that function as being the function that Serderov reverse engineered for